Maybe. All right, so we are moving on to topic 12. Okay. Topic 12 is all about the Earth in general. Now, a lot of this is going to be review, okay, because I did cover a bunch of it at the beginning of the year, okay, but you do need your reference tables, okay? 100% you need your reference tables out on your desk, okay? So, I'll just put this over here. All right, so we're moving on to the second to last chapter. All right? The last chapter is what you guys are doing your projects on. The geologic history, right? That is the last chapter, and it's all about using the reference table. Everything you need to know about geologic history is basically on the reference table, but we'll get to that later. So we're up to dynamic Earth. All right? So Earth's interior, this is going to be review for you, right? Because it's on the reference table, okay? You've seen this picture before because it's the exact same picture that we used at the beginning of the year. Whereas if you broke the Earth in half, right, you'd have the core, you'd have this thing called a mantle, right? You have the crust. You have the oceanic crust versus the continental crust, okay? When you break it down, here it is on the reference table, right? Nothing new. Everything you need to know is on here. The only thing you don't have on here is the state of matter that they are in, solid, liquid, or gas, okay? That's pretty much the only thing you have to memorize about this. Okay, so what's on here? Well, it shows you that we first have our crust and then the mantle, right? That rigid mantle. Those parts are known as the lithosphere. How do I know? It's right here. Okay, you have in between the crust and the rigid mantle this thing called a moho. It's just basically the boundary between the two. You have the density of all of the different sections. Okay, you also have the names. For the outer core and the inner core, you have that it's made up of iron and nickel. Okay? You have that the continental crust is made up of granite and the oceanic crust is made up of basalt. All of this is on the reference table. Okay? Now, talking about the bottom parts. You guys have dealt with the depths before. Okay? I've asked you guys if it's at 1,000 kilometers, what particular section of the Earth are we in, that kind of stuff. Now, I can ask you specifically in the stiffer mantle at 2,000 kilometers, what's the temperature? Just like every other graph, you would go into the stiffer mantle at 2,000 kilometers and go up to the black line. I don't know why I jumped. Okay? And it's going to be more than 4,000 degrees Celsius. I can ask you about the pressure at the same thing. And again, you're going to go up till you hit the black line on the pressure scale, and it's going to be less than 1 million of atmospheres. Okay? Oh yeah, and it's also broken down by these little sections, these dotted lines. That's why I color-coded these, so that you can see them a little bit better. Okay, so we'll start with the continental crust versus the oceanic crust. Right? The continental crust, you should know, it's the land. Right? It's the land that we live on. Then you have the oceanic crust, which is going to be the land under the water. Okay. What's the number one rock that gets made by lava flows? No.
Marble?
What?
This is my feeling.
Scared I'm going to guess that wrong.
You could try.
Bedrock? No.
Not bedrock. So bedrock's at the bottom already. It's already there.
Oh.
What gets created by lava, and the number one rock that gets created by lava as it cools down?
Quartz.
Not quartz.
Okay.
It's like, that's in my
Are we
notes
allowed to play?
somewhere.
Are we allowed to play game right now?
Guys at home, what's your guess?
Coal.
No.
Almost there, wait a second. I really feel like it's obsidian, but
I feel like they are. in this.
Obsidian?
I said that already.
Starts with a B.
The salt?
The salt.
Yeah.
Okay. This is why, guys. What's the oceanic crust made out of?
The salt.
The salt. Okay.
Yes.
So, right? Because all at the bottom here, you have little cracks or little volcanoes on the bottom of the ocean floor that are constantly letting out lava, which hardens into the salt. Okay? There's our favorite. What's the one on the left called? Half dome. Very good. And what is it made out of? Oh, granite. It's made out of granite that got uplifted out of the earth itself. Right? Versus the salt and the oceanic crust. Okay? Right? So, you have this oceanic crust, which is underneath the water. Okay? And then you have the continental crust, right? That is going to be above the water and also it's part of it. So it's above where the continents are. Or I should say it's right below where the continents are. All right, so right now, if we were to drill straight down, up to 70 kilometers down, right, we'd still be a part of the continental crust. Okay? Looking at them, you can tell the oceanic crust is thinner than the continental crust. This is not on your reference table. It is, but it's not easy to see, so you're going to want to write it down. Okay? The continental crust is thicker by a lot. It's up to 70 kilometers thick, whereas the oceanic crust is only 7 to 10 kilometers thick. Okay? The continental crust also has a density that is less than the density of the oceanic crust. Okay? Not by much. It's only 2.7 to 2.9. But again, those specific numbers are listed on the right-hand side of the reference table. Okay? The thickness is very, very, very hard to tell looking at that reference table. Okay? But I can tell you that the continental crust is actually thicker. Okay? The barrier in between the two is known as moho. M-O-H-O. Moho. Okay? Then after that lithosphere, okay, we have the mantle. The mantle is going to be made up of that olivine, or you're going to find olivine and periodotite in the mantle. That's why it's so rare. Because that's underneath the lithosphere. Okay, so you have the upper mantle versus the inner mantle. The upper mantle is somewhat molten. Okay, so it's kind of liquefied, but not completely liquefied. Right? Whereas the mantle is completely solid. Okay, you need to know these guys. You need to know what phase of matter they're in. So make sure you write it down. Okay? Because later when we do earthquakes, you'll find out why we know that the mantle is solid versus the upper mantle, which is semi-molten. Okay, so that's in that, we have that really small layer for the crust that goes all the way around. It's probably as wide as my pinky on this picture. Okay, then we have the Asthenosphere, which is that upper mantle, quote unquote, which is semi-molten. Then the mantle itself is solid. And then, yes, they have been able to prove that they are solid. This is what's made there. This is periodotite, I believe. Okay, you've got the big, thick crystals, right? Because it's inside, right? So it means that it was able to cool over a longer time You get the nice big chunks. And also you have that hint of green going on, right? Okay, so inside of the Earth's interior, I talked about this before, we get those convection cells that are constantly happening. This is kind of what's happening, right? In convection, if you're by the heating source, what happens to the molecules when you're by the heating source? They expand, but before they expand, what do they have to do? Before they spread out, what do they have to do?
Move quicker.
Move quicker, right? They're moving quicker because they increase the temperature, which means you've increased their average kinetic energy, so they start to move more, and they rise up. As they rise up, they spread apart, right? But once you get away from the heating source, you start to cool down, right? So the further away they get away from the heating source, they cool down. When they cool down, that means that their kinetic energy slows down, right? There's less of it, which means that their density increases and they fall back down, creating that convection current, right? And you have to remember, with convection currents and convection cells, right, wherever the heating source is where you're going to go up. Then you move away from the heating source, come back down, and back in. If the heating source is in the middle, right, you can have two convection cells where they go up, away, down, and back, like in this case. Right, you have two convection cells that are happening because they're by the heating source. Now, this is what I was telling you about, where it says this little under the wall. Well, I think this one is actually on the continental crust in this picture, but you have volcanoes, right? You also have volcanoes at the bottom of the ocean that constantly are erupting. Every time that they erupt, or those cracks in the ground, and allow lava to come out, you create new land. Okay? So these convection cells are basically happening inside of the mantle and the Asthenosphere. Okay, so that upper mantle and the mantle. Okay? But they're happening naturally. All right? So if you see how it says a rift valley on a ridge crest? You see how it's open like that? That's a little opening inside of the crust that allows the lava to come out and escape. Okay? We've gone over convection currents a million times by now. It's kind of a review. All right? So let's talk about the core. What does Ni stand for?
Nitrogen.
No. N is nitrogen. What does Ni stand for? No.
Nickel?
What?
Nickel?
Yes, it's nickel. Good. And what does Fe stand for? Good. You all knew that one. If you weren't sure, guys, look at your reference table. Right? On the last page of the reference table, you have a bunch of symbols that are there. I guarantee you that nickel and iron show up there as well. And if you're not sure, we're also talking about the core. And on the reference table, page 14 that I showed you before, it says underneath it for the core is made up of nickel and iron. Okay? If you're talking about the outer core, it's going to be liquid. Again, you need to know this. Okay? The inner core is solid. Again, when we do earthquakes, I'm going to show you how they prove this to be true. Okay. When you break it down, it basically looks like this. You have your inner core in the center, kind of like those Russian nesting dolls, you know, the ones where you keep opening them, and then at the final you have like a little tiny doll. But now we're talking about the Earth, so it's like the little tiny ball in the middle is the inner core, which is solid. Then you have the outer core, right? Then you have the mantle. And then look how thin the crust is in comparison to the rest. Okay? The crust is super thin in comparison. And if you go back to page 14 in your reference table, okay, you can also see it because the little pieces, the little dotted lines as it goes down, the crust is much smaller than the rest. Okay? All right, so I'm going to show you this little video on how to use your reference table with this, because I thought since you guys are having so much trouble with it, it might help you. Let's see if the internet wants to work. Make sure you guys are following along. I want you guys to have your reference tables out, and I want you to do it with them so you have an understanding. You know, if it wants to work. Work. Please work. Pretend like you like me, technology. That's the next thing I'm doing.
Screen blacked out.
That's fantastic. Now it's white out. Okay, why does this always happen to me? Every time I try to show you guys a video. Okay. This is a 5-minute video. It's going to take 10 minutes to load.
For just $67.
And there's
you
a
can make
commercial.
as many videos as you want, and you never need to pick up a camera or you.
Hi everyone, welcome to the Earth Science Research Review podcast series created by Huntington Middle School Earth Science Department. Today we're going to talk about page 10 in the reference table, the inferred properties of the Earth's interior. Now the reason why it's called the inferred properties chart is very simply because we haven't dug a hole anything within 7.5 miles of the Earth. So the majority of our information comes through the study of earthquake waves and meteorite studies. So let's start off with the different layers first. The outer portion of the Earth is what we call the crust, and that's going to be indicated by the black outer line. Below that is a white line labeled the rigid mantle. Together, they make up what's called the lithosphere. Below that, you have the silly putty-like asthenosphere, and that's why it's called the plastic mantle, very simply because of its fluid-like properties. Because the heat is a little bit greater inside the Earth than at the surface at this depth, okay, that layer is going to be influenced by the temperature differences, which is ultimately going to affect the density. The density differences within a layer is what we call convection. Now, there are two convection cells. You have one portrayed on the west coast of the United States, where the Wandeputla plate is converging with the North American plate, producing the Cascade Mountains. And we also have one in the middle of the Atlantic Ocean, producing the Mid-Atlantic Ridge. This is a divergent plate boundary. Okay. Below that, you
Just so you guys know, when he's talking about divergent and convergent, they're talking about Earth Science Reference Table, page 5, I believe it is. Convergent just means that they're going towards each other and one goes underneath the other. Divergent just means that they pull apart. Okay?
You have the stiffer mantle. Below that, you have the outer core, made up of liquid iron and nickel. Below that, you have the inner core, made up of solid iron and nickel. Now, you notice that each layer has its own individual pattern. So that represents where one layer ends, the other one is going to begin. So the very outer portion of our Earth is the lithosphere. Where the lithosphere ends, the asthenosphere begins. As we travel deeper, where the asthenosphere ends, the stiffer mantle begins. We travel deeper. The stiffer mantle ends, the outer core begins. Where the outer core begins, the inner core begins, and we can go as deep as the actual center of our planet. Now, each layer actually has its own distinctive density range. So you see that the lithosphere, specifically the crustal part of the lithosphere, goes between 2.7 and 3.0 grams per cubic centimeter, based on what type of crust you're dealing with. You notice that there's a little boundary between the crust and the rigid mantle. That's called the moho, which indicates that there's a stark density difference between those two layers. Earthquake waves not only change direction, but they also change speed as well. They speed up as they exit the crust and enter the rigid mantle. The Stenosphere, which is technically on the upper portion of the stiffer mantle, they're going to have a range between 3.4 to 5.6 grams per cubic centimeter. The outer core is 9.9 to 12.2 grams per cubic centimeter, and the inner core is 12.8 to 13.1 grams per cubic centimeter. Now that's the upper portion. Let's move to the middle section. And this is basically going to represent the pressure. Now you notice this section looks like a direct relationship, if we were going to graph it out. Okay, the dark reference line is an upward sloping line, just like a direct relationship is. That's the relationship between pressure and depth. As you go deeper into the planet, the higher the pressure, just like with density. The deeper that you go on the planet, the higher the density. Okay? In this case, what you're going to do is you're going to extend your boundaries or your interfaces down until they intersect your black reference line. So we're going to take the lithosphere, the top of the lithosphere, bring it straight down. Okay? You can see that your pressure is 0, but you notice your units here, it's millions of atmospheres. Basically what this does is it measures what the pressure is like, how many millions of times greater it is inside the Earth as it is here at sea level. So on the lithosphere, we're at sea level, your pressure is going to be 0 millions of atmospheres. Extend the bottom of the lithosphere down, okay, you're going to have a pressure of about 0.1 millions of atmospheres. So there is your lithosphere. Where the lithosphere ends, the asthenosphere begins. The asthenosphere will begin at 0.1 millions of atmospheres and extend down to about 0.2 millions of atmospheres. So there's your asthenosphere. Where the asthenosphere ends, the stiffer mantle begins. 0.2 millions of atmospheres to about 1.5 millions of atmospheres. So there's your stiffer mantle. Where the stiffer mantle ends, the outer core begins. 1.5 millions of atmospheres to about 3.1 millions of atmospheres. There's your outer core. Then where the outer core ends, the inner core begins. Okay, the inner core is going to begin at 3.1 millions of atmospheres, and the center of our planet is roughly 3.6 millions of atmospheres. Again, that's going to be the inner core there. That is the arc pressure. As you go deeper in the planet, the pressure increases. Now you're going to do the exact same thing with your temperature. You're going to extend the interfaces straight down until they intersect your black reference line with temperature. Again, direct relationship. The deeper you go on the planet, the hotter it gets. Now notice that your temperature is in degrees Celsius. So the lithosphere, at the top of the lithosphere, is going to be about 0 degrees Celsius. The bottom of the lithosphere will be about 1,000 degrees Celsius. There's your lithosphere. Where the lithosphere ends, the asthenosphere begins. So the asthenosphere is going to begin at about 1,000, and it's going to extend to about 2,600 degrees Celsius. There's your asthenosphere. Where your asthenosphere ends, the stiffer mantle begins. 2,600 degrees Celsius to about 5,000 degrees Celsius. There's your stiffer mantle. The stiffer mantle ends, the outer core begins. 5,000 degrees Celsius to about 6,200 degrees Celsius for the outer core. Where the outer core begins, the inner core, where the outer core ends, the inner core is going to begin. 6,200 degrees Celsius to approximately 6,600 degrees Celsius at the center. Again, that's going to be approximately our inner core. So again, you notice it's a direct relationship between depth and temperature. Now you do see a couple dotted lines that are labeled melting points. Anytime the melting point is below the interior temperature, you're going to have a liquid layer. Okay, the interior temperature, when it's above the melting point, means the melting point has already been reached. That's going to be a...
Did you guys get that? You guys wrote that down, right?
Wait, could you repeat what it was?
Yep.
So again, you notice it's a direct relationship between depth and temperature. Now you do see a couple dotted lines that are labeled melting points. Anytime the melting point is below the interior temperature, you're going to have a liquid layer.
Okay, so anytime you see that this melting point is below the interior temperature, right, it means that it melted before it reaches the interior temperature, so you're going to have a liquid layer. You remember how I said the asthenosphere or the upper mantle was partially molten layer, right? Look down here. Here's the asthenosphere. Here's the melting point, which is just below, barely, the interior temperature, which means that it's going to be partially molten.
Okay, the interior temperature, when it's above the melting point, means the melting point has already been reached. That's going to be a liquid layer. You notice what layers they are? The asthenosphere and the outer core. So if the melting point is below the interior temperature, you have a liquid or semi-liquid layer. The last section we're gonna deal with is depth. Okay, and again,
So before he does that, right? So in the layers where the melting point is above the temperature, right? That means that the melting point, in order to reach it, you need to increase the temperature in that layer. You are going to have a solid. Look where they are. You're talking about the mantle itself and the inner core. Okay?
and bring the boundary points directly down to where they're going to intersect your depth range. So the lithosphere begins obviously at sea level and extends to a depth of about 100 kilometers. There's your lithosphere.
You might want to write down the depths for each of them, because for the lithosphere especially, it's a little bit harder to tell that it's from 0 to 100 kilometers deep, approximately. So like we're talking about with the lithosphere, you're talking about the oceanic crust and the continental crust. They're about between 0 and 100 kilometers.
Okay, your asthenosphere is going to begin at about 100 kilometers and extend to about 800 kilometers.
Okay, so for the asthenosphere, we're talking about between 100 and approximately 800 kilometers deep. Just so that you get an idea as to what the depth should be and how to read it. So it's between 100 and 800.
There's your asthenosphere. Your stiffer mantle will begin at about 800 kilometers and extend to about 2,900 kilometers.
You said 800
800 to 2,900. Right, so it's always going to start where the other one ended.
Here's your stiffer mantle. The outer core will begin at about 2,900 kilometers and extend to about 5,100 kilometers.
So 2,900 to about 5,100 for the outer.
There's your outer core. And finally, your inner core is going to begin at about 5,100 kilometers and extend to about 6,300 kilometers.
So inner is 5,100 to about 6,300 kilometers deep. So that's how far down you'd have to go in the earth to reach the inner core. You would start reaching the inner core about 5,100 kilometers down, but it pretty much ends at 6,100 kilometers, or we get to the center of the inner core at that point.
Okay, so that's essentially the inferred properties chart. A lot of information here. Make sure you know how to read it. Thanks so much. We'll talk to you soon.
Okay. This
If
is
you want to know why,
no. Go away. We don't want to know.
But I do.
No. Okay. If you guys want to see that video again, I can post it for you. If not, he's also the guy I've been telling you guys about for Comics Middle School, or Science Reference Table. It's Comics. It's HAMMOCKS Middle School. He does a lot of really good videos for all of the Earth Science Reference Table pages, for reviews in general, for little clips. And you saw they're pretty short, but he explains each of them. So if you're having trouble reading the reference table, definitely check him out. All right, so what I would like you guys to work on is review book pages 258 to 259, questions 29 to 41. This is going to be practice on using your reference table and what you just learned. What's up? 12. Yeah.
Miss Gonzalez,
Yeah.
what did he say for stiffer mantle? I didn't catch that.
What part? The depth?
For the
2,900.
800 to 2,900. I'm going by what they just told me.
thank you.
You're welcome.
So you know what I just noticed?
What's up? Okay, so hold on. We are going to be working on those pages. Whatever you don't finish, I want you to complete for homework so that we can go over it. Remember, when you are doing practice problems, explain why the other 3 answers are incorrect. Okay, if you do that, it will help you. Are you going to stop recording now?
You want to know something?
Hold on.